Welcome, everyone. It's my honor to chair the last session of this fantastic conference. Our first speaker is Leah Santos from the Department of Physics, University of Connecticut. She'll be talking about spectral kissing and its dynamical consequences in the squeeze-driven Kerr oscillator. I think we have the audience mature enough for this title.
Okay, so I'd like to thank the organizers for this invitation, you all for coming. Before I start with this talk, which is described in the abstract, I just wanted to mention to you this other work that we have with Pragya, Devendra, and Aditi, which is very much aligned with the theme of this program. It has the similar title, no? It's periodically and quasi-periodically driven, in our case, the decay model. So Pragya has a poster here, so I'm just going to highlight the results. What we saw is that when we drive this system quasi-periodically, we see this kind of pictures that is familiar, no, in driven systems, with a plateau here that is followed by heating when the system reaches this infinite temperature state. What we did was to study how this plateau increases with the frequency. It increases exponentially, either exponentially or square root of the frequency, depending on the protocol. And we also did this analysis with the energy of the initial state. So this plateau gets higher as the energy increases, which is expected. But now, when we drive this system periodically, we don't see that. We don't see these two features. And the system just saturates and it doesn't heat up. So of course, this saturation point depends on the energy of the initial state. So this is low energy, high energy, depends on the frequency, depends on the parameters of the Hamiltonian. If this Hamiltonian, the undriven Hamiltonian, is in the chaotic or non-chaotic regime. But we never saw the second step in this story. So if the system is kind of protected, no? If it's periodically driven, it's protected against heating. And then another discussion that appears in this work is how to change the critical point from the normal phase to the super radiant phase with a drive, and also a discussion about the problems that we have doing level statistics when we have quasi-energies. Okay, so if you haven't seen the poster yet, Pragya is still here, so you can come to her poster. Okay, so I'm going to now start with the talk, that is described in the abstract, the spectral kissing. So this is a collaboration with different people. I'm showing here just the pictures of the postdocs. So Jorge, Thalia, and Rodrigo, and the PhD student Jaya. So Rodrigo and Jaya, they are part of Michel Devoret's group. So this is an experimental group. And we are all part of a bigger center, one of those NSF centers. So the description here will be about the Hamiltonian that describes the system. So let me go step by step to explain to you the experimental setup. So suppose we have a single atom which is excited. Well, we know that after some time, it will get rid of its excess of energy. So that's the idea of spontaneous emission. Okay, so now let's put this atom inside a cavity. So now we can control this emission. So this is a good environment to study the interaction between light and matter. Okay, but what the group does is instead of an atom like this, they put an artificial atom. So what is that? Is a circuit. What kind of circuit? Well, if it was LC, the inductor and the capacitor, we would be playing with a harmonic oscillator. This is small system, low temperature, so we have a quantum harmonic oscillator, where the flux here would play the role of position and the charge would be the momentum. But that's not yet what we have, or what the experimental group has. Instead of the inductor, they put there a Josephson junction. So the junction is this nonlinear element of the circuit. And what do we gain with this? Well, instead of having the harmonic potential x squared, we now have cosine of x. So we now have a pendulum, a quantum pendulum. And what we are dealing now with is a quantum anharmonic oscillator. The big advantage is now the levels are not equidistant anymore. So the levels are now addressable, and we can focus on the two lowest levels. And here we have a qubit. So this is the transmon qubit that was developed in the Devoret's group. But what are they doing now? They are focusing on this Snail transmon and not just on these two lowest levels. They are looking at the higher levels as well. And this system is driven. So what we have is this driven superconducting nonlinear oscillator described by this Hamiltonian. So this is the nonlinearity and the driven part. So what is this? Is a parametric oscillator. Someone who has worked a lot on this kind of systems is Mark Dickman. He has a sequence of works, a book about that. And one of the scenarios that Mark has played with, okay, so many of the things that Mark predicted has now been verified by these experiments. But one of the scenarios that he works a lot with is this one where the frequency of the drive is twice the natural frequency of the oscillator. So this now gives us this double well. So the system is described by this double well. If you go in a rotating frame, you can get an effective Hamiltonian for this. This was done by Jaya. And so this is the effective Hamiltonian that describes very well the driven system. And the focus of this work will be on this effective Hamiltonian. Now, so we have two competing terms. This is the nonlinearity, the Kerr term, and this is the squeezing amplitude. So you see, it's a simple system, not just 1 degree of freedom. And you see that there'll be interesting things coming out from this. So this is pictures coming from this experimental work. So what they got is the levels, the spectrum as a function of this control parameter. So the control parameter is this ratio between the squeezing and the nonlinearity. So this is from the driven system, these purple lines. This is what we get with the theory, with that Hamiltonian, and you see very good agreement. No? If you put both together, you see that they are on top of each other. So what are the nice features that we are seeing? You see that there are two levels here that are getting closer as the control parameter increases, and then they merge together. And then you pick the next two levels, the same thing, but for a larger value of the control parameter. So this is what they are calling spectral kissing. So cute name, catchy name, but that's when we come into the game to say, well, this feature, spectral kissing, is what was known as excited state quantum phase transition. So this is the experimental work, and this is the theory. Now we are not restricted by the experiment anymore. I can show to you many levels, and you are seeing that they are all merging together along this orange line. So this Hamiltonian conserves parity. So I'm showing to you in black levels from the even parity sector, and in red, the ones from the odd sector. So you go even, odd, merge together, even, odd, merge together along this line. Now, even if I make the plot with just levels from one sector, I still see something happening along this line. You see there is a clustering of the levels along this line. So if I now make cuts, vertical cuts, get all of these eigenvalues, I can look at density of states. So if I make the cut for a small value of this control parameter, I see the peak showing up here at a low energy. If I pick not the value of the control parameter, I'll see the peak showing up at a higher energy. Now, so this peak, this divergence in the density of states is a main feature of what became known as excited state quantum phase transition. It's not a new subject, but the community used to be small. It's growing, I think, now, but not many people knew about, so the experimental group didn't know about that. But it's not exclusive to this Kerr Hamiltonian. It shows up in other systems. So, for example, the Lipkin, the LMG model. So this is the Hamiltonian for this system. SZ here is the sum of all the matrices in the Z, and this is the sum in X. We can see this system as a single big spin, n/2, or you can see this system as a sum of many spins half, similar to this kind of system that has been studied with ion traps. But now instead of just long range, we really have alpha 0, no? So all-to-all coupling. So it's a collective model. So seeing this model from this perspective of many spins half is what was done in Vladan's group. So they realized this Lipkin model, but with many, many spins half, all-to-all couplings. And I'm going to come back to this experiment later. Okay, but what we know about the Lipkin model, two competing terms, just as in the Kerr, C0, Z only, so the spin is in the Z direction, C1, X only, and now the generous, is X squared, so the spin is either up or down in the X direction. As we increase this control parameter, the ground state and the first excited state eventually merge together, not collapse. So this is the point, the critical point for the ground state quantum phase transition. Well, we can look at the higher levels as well. And you see a plot very similar to the one that I showed to you before. So the Hamiltonian also conserves parity, and we see even odd getting together. So this line here is the line that is the line of the excited state quantum phase transition. It's a line that is separating this region that is dominated by the X term from this region that is dominated by the Z term. So very similar to the Kerr Hamiltonian, the difference is that this spectrum is bounded and the other one was unbounded. There are other models that will show the same thing. So these are models that have been used to describe molecules. So below we have a bent molecule and above a ridge molecule. So these models have effectively 1 degree of freedom. If you go to a system with 2 degrees of freedom, like the decay model, you're not going to see the divergence in the density of states. You have to look at the first derivative. And if you go higher or systems with more degrees of freedom, then you go higher orders in the derivative. Okay, so this is the idea. Let's come back to our Hamiltonian, the Kerr Hamiltonian, and tell you a little bit more about some features that we see along this line. So when the control parameter is 0, so we don't have the squeezing, we have just this term, the ground state here is the Fock state 0. Okay, but if I pick an eigenstate at the ESQPT, you see that this eigenstate is still very much localized in the Fock state 0. How do we know that? Well, we look at the structure of the eigenstates. Now we write these eigenstates in terms of the Fock basis. And then we go on looking at these components as a function of the energies of the Fock state. So if I pick a state with low energy below the ESQPT, you see many, many contributions. Above, again, many, many contributions, now from low and high energies. But right here, you practically have just one dot there. So highly localized in the Fock state 0. Many of you know now the participation ratio is a way to measure how much delocalized a state is. Participation ratio large, delocalized state, small, localized state. And you see at the energy of the ESQPT, where we have the divergence of the density of states, the thing really falls and falls very close to 1. All right, so how can we understand these features that we are seeing? A good way is to go into the classical limit. This is the Hamiltonian in the classical limit, and let's see how this can help us getting some analytical results. So what I'm showing here is I select a value of Q and P, and I color this panel with the value of the energy. So bright yellow means low energy, means we are below here at the bottom of the well. And as it gets darker, that means we are going higher in energy. The 2 wells meet at this point, which is this point O that we are showing here. So this point O you see is a saddle point. Now you go down in energy and you go up here. So this is a saddle point. With this classical Hamiltonian, we can obtain the stationary points, and we know what they are. They are just 3, the 2 minima here, and that point, the point O, the saddle point, the hyperbolic point, where P and Q is 0, right at the origin of the phase space. So let's use that now to explain what we are seeing here. The degeneracies that we are seeing below the ESQPT is equivalent to what we are seeing here. Now we have 2 trajectories that have the same energy. So we are inside the wells, so we have degeneracy. When we reach this point, we are at the saddle point, the hyperbolic point, and above, we are above the 2 wells, so no more degeneracy. So this line that we have here is the line that separates the 2 phases. So this line, this point here is the separatrix that we see there. Now, what is this orange line? Is just the energy difference between the energy of the saddle point and the minimum. So now we have this analytical result, and this is the expression, this line that I've been showing before. How about the localization of the eigenstate here? Well, right here is the stationary point. So my eigenstate is localized at this stationary point. This stationary point is P0, Q0. So that's the Fock state 0. To make a better connection between the structure of the eigenstates and phase space, better than looking at the structure, better than looking at the eigenstates in terms of Fock basis, let's project the eigenstates in the coherent basis. So now we have these weights. So we are going to see how we are going to look at the Husimi function to see how the state is spread out in the phase space. So we selected 4 examples, one low energy. So down there we have these 2 circles. They're not circles, they are like ellipses, just as we have in the phase space in the classical limit. Go high in energy, the ellipses grow. Once we reach that point, strong localization in the Fock state 0, which is the same thing as the coherent state P0, Q0. And above, well, high energy, then we are surrounding all the 3 points. Okay, so the last thing to talk about this classical Hamiltonian is that we can use it to obtain the density of states. So this blue envelope here is what we get from the classical limit. Now that we are well prepared, let's see what is more interesting, which is the dynamics. So we selected here 6 initial states. They're all coherent states, each one centered at a different letter here. So one center at the center here, the P0, Q0. B has energy slightly below, C is slightly above, A is very boring, close to one of these minimum. And D and E have high energy. And they have the same energy, but one is far from the separatrix, one is close. So we are looking first at this survival probability, the probability for finding the initial state later in time. And this is the plot. So the first thing that we see is that state, the coherent state O, has the slowest decay. Now it has higher energy than A, but it's much slower than A. And why is that? We know, is what we already said, is localization. No? The eigenstate at this energy is localized in that coherent state O. So that coherent state O is almost like a stationary state, so it's decaying very slow. Next to it comes B and C, because they are very close to that stationary point as well. So they are slower than point A. And then finally, D and E, they have high energy, so survival probability decays really fast. Interesting though that they have the same energy, but E is decaying even faster. And why? Well, the energy distribution is different, E is broader, and this is related to the fact that E is close to the separatrix. Good, so this is survival probability, easy to understand. Let's now compare with another quantity, which is the out of time order correlator. So, well, you know this quantity, the commutator between 2 operators at time 0. It's either 0, very small, and the commutator grows as time grows. So it was a quantity that supposedly was a detector of chaos in the quantum limit. So, and it's true, this has been verified by many different works. When the system is chaotic in the classical limit, the talk shows this exponential growth. The rate coincides with the classical Lyapunov exponent. So this was shown by Galitsky for the kick rotor, for the billiard. We showed this for the Dick model, the other studies. Good. So let's have a look at the talk for our Kerr system. I'm showing to you the photok, which is the variance of the coordinates, just because this is more accessible to the experiments, but the results for OTOC are the same. Okay? And what we are seeing an exponential growth for that state O, for the coherent state O. And how is it possible that we get an exponential growth? This system is regular, no? So we have a time-independent Hamiltonian, just 1 degree of freedom, so there is no way we could have chaos. So where is this exponential behavior coming from? Well, the idea is simple, no? Suppose you have a pendulum, this is a regular system, but once you invert it, you reach an unstable point. And so you get here a positive Lyapunov exponent. We got this positive Lyapunov exponent, but this has nothing to do with chaos. There is no mixing after that. It's just instability. So that's what this exponential growth is detecting, instability. Yeah? And again, matching very well the Lyapunov exponent. This is what we wanted the experimental group to do. But, you know, experimentalists have their priorities. But at least this was done by Bladen's group. So that's why I was mentioning to you this work. So they checked the autark for the Lipkin model, and right there at the critical point, you get this exponential growth. Okay. All right, let's come back to the plot for the photalk. You see that also state B, C, the ones very close to the unstable point, and state E, which is very close to the separatrix, they also have an exponential growth. Not for as long as O, but they also show an exponential growth. And where is this coming from? Well, these are coherent states, no? So they have a width. It's not just a point E. Now, if you would start classically, right at point E or right at point C, you wouldn't see exponential growth. But this, since it has a width, it captures that instability. So you get that exponential behavior. Okay? So it's like a quantum effect, or it's caused by this uncertainty. All right. And then, okay, so then A, of course, I don't need to tell you, it's super boring, it doesn't spread.
So what would be the effective H bar size on that?
Right, so as H bar, if you go closer and closer to the classical limit and your coherent state gets smaller and smaller, this exponential behavior will be disappearing. But
on that plot, for this particular plot, you have effective H bar.
Right.
So how large would that be on that?
How large the width is here. I'm going to show to you a snapshot, but yeah. Okay, so very boring, A. And then the state D, which is not close to separatrix, but has high energy, it goes on evolving slowly with these oscillations. All right, so now I want to put both results together. And if you look at both, it looks like a paradox, right? Because the survival probability for coherent state O is the slowest one, but the photalk for state O is the fastest one, or remains in this exponential for longer. So how can we understand these two? No? So this is a nice thing, is showing different quantities, show different behaviors. No? Quantum dynamics depends on the quantities, of course. But how can we understand what is going on here? So now I'm going to show the snapshots of the Husimi function. So now it's Husimi function for the state that is evolving. So this is more or less what you asked. So this is time 0. So this is their width, yeah? Okay. So, so I'm showing snapshots. We have nice videos, but we never know if the videos will work. No? So I picked just some times and just 3 states, the state O there at the unstable point, and D and E, which have high energy. So for very short times, you see that states spread out really quickly, faster than the others. And what is going on, how we understand that? At the origin, the dominant term for the dynamics of these states is the squeezing part. So it's really squeezing it really fast. It's stretching it. It's like a rubber band. So this explains that exponential behavior. No, the other ones are slower. Okay, so exponential growth of the photalk. But how about this low survival probability? The issue is that, remember, this is a stationary point. So the state would want to be there. So, but it's being stretched by the squeezing part. It's being stretched, but a portion of it survives there. You see, there is always a piece inside. So that explains why the survival probability is so slow. While these guys, they came out completely from their initial state. So the survival probability went down to 0 very fast. Okay, some details about like state O. It spreads really fast, but then it comes back. Spreads really fast and comes back like a yo-yo. No? So is this scrambling? As a question for you. The state E, this is the best. It takes the best from both worlds if you think about scrambling. It has fast spread because it's touching the separatrix, but it also has large energy. So it's spreading inside the separatrix, outside. You soon have this nice quantum interference. You get this nice plot. So this state is more spread out at long times than the state O. For D, you also see similar things. Okay, so that's my question to you. What is scrambling? If we are thinking just about very short times, true, O is spread out more. But if you look at long times, O is stretching and compressing, stretching and compressing, has these big fluctuations, and it saturates down here. while state E and even state D, we didn't have this initial exponential growth, will saturate much higher and with almost, well, small fluctuations. Okay, so these are the results from this paper. I just wanted to advertise a little bit of the experimental platform. Tell me. So the high energies, oops. The system is regular, okay, but we get these quantum interferences, but the system here is regular. We didn't do this for this model, but we did some comparisons with quantum classical for other models, like the decay model. And yes, the behavior is very similar at short times. Yeah, at very long times, for the decay model, in the chaotic regime, there are some features that show up because of spectral correlations that we don't see in the classical union. I can show this to you, and that's kind of interesting. Yeah? But we didn't do this here. Okay, so advertising the experiment. Now, so what the group is mostly interested in? Well, they're interested in quantum information. Now, so getting these degeneracies for them is very interesting because they can create these Schrödinger's cat states, which are very robust. They have done already for the ground state. So that's their thing. No? So these states are robust. They can use it as logical states for qubits. But you see, once we start looking at higher energy, there is more to the system. In this case, for example, we are looking at energy as a function of the control parameter. So this is a good scenario to study excited state quantum phase transition. The studies about ESQPT that have been done in the past were mostly focused on molecules. So a molecule is at a fixed control parameter. Now you cannot study it as a function of the control parameter. The other advantage of the system is that they have both. They can measure both spectrum and dynamics at the same time. Usually you have one or the other. And there is dynamics in phase space. Okay. What else can we do? Well, by tuning those parameters in the driven Hamiltonian, you can have other terms in the effective Hamiltonian, such as this one. So this Hamiltonian has been studied by the experimental group, and I'm just going to describe to you some results from the theory. Okay, so, it's here. Okay, good. So, okay. So once we have this delta term, we get different phase spaces depending on the value. Delta negative is boring. No, I didn't even tell you about this. Delta 0 was the one with one hyperbolic point. But once we go delta larger, there is a whole region here, we now get two hyperbolic points with a local maximum now in the middle. No? So it's the hyperbolic splitting two. A better idea. Without delta, we had those two wells with the saddle point here. With delta, we have the two wells, but they meet now in these hyperbolic points. No? And now we have two additional interesting regions, which is the region of the local maximum and around. So we can have states here and around that may have or not the same energy. Sometimes they are degenerate. So this is what I'm showing now to you here. The levels for this kind of scenario. So low energies, similar to what we had before. We are the bottom or inside the wells, degenerate. Once we reach the hyperbolic points, excited state quantum phase transition. Now, between the purple region here, we start seeing some crossings until we reach the maximum of the local maximum. That's another ESQPT, and above that, no degeneracies anymore. So again, for the experimental group, this is an interesting region. Let me go next. Again, for those cat states, but also some analysis of tunneling. Density of states. In addition to that peak, we now have this discontinuous step, so two ESQPTs, and the interesting things are happening in between the two at those crossings. So look at this. I'm picking just a piece of that. you will see that the crossings happen only when this ratio is an integer value. So where are these crossings coming from? It's some kind of local symmetry that we are still trying to understand. It has memory from this part of the Hamiltonian. Those crossings for this Hamiltonian are at the same point, but they survive even when you put the squeezing at the same points. Now, some are real crossings when you play with, when you have even and odd, and some are avoided crossings. Oh, it's already 5 minutes. So these will have effects on the structure of the eigenstates, odd, if we are that region of energy in and out, we'll have contributions from both sides. When it's even, it's either out or in. So these features will have consequences for the studies of tunneling. When we are odd, and I start with a state outside, as it spreads, it can get inside and it spread outside, both. But if it's even, it only spreads outside. Okay, so we can see these peaks. We use some Monte Carlo simulation, define quantities to measure this tunneling inside the region, outside the region, and we see these peaks only when it's odd. So you could get a sense of whether the system has real crossings or avoided crossings by looking at the dynamics. Okay? But I want to skip this. This is the experiment. Again, they get spectrum and the analysis of tunneling. But I just want to come to this last slide to tell you what is next. Now, the system that I showed to you is simple, just 1 degree of freedom. But I think what is next will be the most exciting thing. Okay? Of course, there are things to include there, this discussion about symmetries, including dissipation. But what I'm mostly interested in is chaos. Depending on how we drive the system, it becomes chaotic. We already have some results, and we are just putting them together. But this, I think, will become very interesting because now is the melting of the transmon as a device to study as a qubit or as a qubit, but it's the birth of the transmon as a chaos detector or entity to study chaos. And I think also what is very interesting is coupling the oscillators. This is where the experimental group is moving towards, and also we are going to try to follow now. So this will be really many body systems to study. So then with that, maybe I come back to my correlation holes and relaxation time, the things that I've been talking about. Okay, so thank you for your attention.
Thank you, Leah. Questions?
Thank you. I was noticing that these models, because they're all one-dimensional, would be things where you could approximately solve the quantum problem by using WKB approaches. Is that something that's been done to do comparison?
Mark Dickman has many studies about that. Yeah.
Okay.
About these phase transitions, steady state phase transitions, they have different types of order, like first order, second order. I saw jumps you had, and can they be classified in terms of universalities?
It has all been classified. The main person who has done this study is Pavel Sejinar. I can show that they have a review paper from 2021, but our case is second order.
Is there any way they can affect thermodynamics, or is it has to be like energy selected responses, or
that I don't know, but this is quantum. No, it's because it's happening at a specific energy. So I don't know. Maybe there is some discussion in their works.
Thank you.
It's last same question. Yeah, so, I mean, so like in this kind of experiments, it seems like you should be able to see the classical quantum correspondence very directly. So since one can measure the Wigner distribution as a function of time, I guess. So I mean, are there like at high energies, I would expect that it should stay localized and it should follow the classical path. I mean, is that something that's been?
As I said, we didn't do for this model, although it's all quantum classical. No? You could look at the orbits, but we did that for another system. this quantum classical correspondence.
But here it also you should have it,
You
right?
should-
If
you
you look at
should-
high energy.
Yeah, you should have the same.
Maybe a related question. Did you look at Wigner function evolution when you started with these coherent states and ask how quickly do you get negativity? And is that very different for different initial conditions?
We didn't, just because the Husimi looked nicer, okay? But if you go to the experimental work, they do have the Wigner, and you can see the interferences showing up and positive and negative. The analysis of when this shows up or not, we didn't do, but yeah, would do.
From a quantum information point of
Yeah.
view, that's definitely a resource to have these negative Wigner functions.
But if you look at their papers, they show figures of Wigner. For us, I thought it was more beautiful to show Husimi's.
Other questions?
You showed, so the starting model was, after you did this rotating wave approximation, was not still conserving the number of particles. But then you went to a spin model, Sx squared plus Sz or something like that, which does conserve the number of particles, right? Now that one you can again map onto some kind of Bose-Hubbard model on two sides, which also conserves the number of particles.
It's the same.
Now I was wondering, what are these two sites or these 2 degrees of freedom in the original driven anharmonic oscillator?
From the Bose-Hubbard.
Well, no, what I'm trying to say is after I do all these steps, I end up with some similarity to a 2 degree of freedom Bose-Hubbard dimer.
Okay.
So
but still, if you go to the Bose-Hubbard, you have conservation of energy, you have conservation of number of particles, so you still have 1 degree of freedom. I can show to you, and we have the map.
Sure.
You have 2 variables only.
Right, but you showed this at some point. You showed a spin Hamiltonian.
Yeah,
with
that is
which also
also 1
conserves
degree of
2.
But it's 1 degree of freedom still.
Yes, but well, no.
It is.
Okay, maybe we should discuss later. Thank you.
Are there more questions? If not, let's thank Leah for a very interesting talk.